We now know that for some polynomial p of x, that c is a zero or a solution of that polynomial if and only if x minus c is a factor of the polynomial. If x minus c is a factor, then we can use synthetic or long division to divide that polynomial p of x by x minus c, and then we can write p of x of the form x minus c times whatever that quotient we get is. And notice this is one factor, and now this is a second factor of lower degree. So that's one way we can factor polynomials now. But what we still need is a way to find these c values so we can get these factors when it doesn't factor easily. Because we can't use synthetic or long division until we know at least one zero, and we don't have anything like the quadratic formula to help identify all these zeros once we get into higher degrees. What we're going to look at today is a method called the rational zero theorem that allows us ways to check zeros. It doesn't give them to us, but at least gives us a list of where to start checking. The rational zero theorem says if we're given a polynomial with integer coefficients, and that's important, then any rational zero has to be of the form p divided by q, where p is a factor of a naught, and remember a naught is the constant term, and q is a factor of a sub n, which is the leading coefficient. Please note that this doesn't always find a zero, but rather it identifies possible rational zeros that we can check. If we still don't get any, there still could be irrational or complex zeros that this method does not find. So let's look at what this means. If we want to list the potential zeros of a polynomial, consider the polynomial f of x is equal to 2x cubed plus 5x squared minus 4x minus 3. The rational zeros theorem says they have to be of the form p divided by q, where p are factors of -3 and q are factors of 2. So we need to list the factors. I like to write it of the form plus or minus. The factors of p are 1 and 3, positive or negative, and the factors of q are positive or negative 1 and 2. Again, we're factoring this term and this term. So we can then list those factors as 1 over 1, which is just 1, 1 over 2, 3 over 1, which is just 3, or 3 over 2. Notice this gives us 2, 4, 6, 8 possible factors now. And then we can use synthetic division to check them. Because remember, synthetic division tells us that if we take a number, so let's start with 1, and let's use synthetic division. So I'm going to write the coefficients there. If my remainder comes out to be 0, then I know I have a factor of that polynomial. I drop my 2, 1 times 2 is 2, which leaves me with 7. This gives me 1 times 7 is 7, which leaves me with 3. 1 times 3 is 3. When I subtract those, I get 0. So what this tells me is x minus 1 is a factor. I can go back and rewrite this with lower degree, which this is my constant. This is going to be my x term. This is x squared. So I can now write this polynomial 2x cubed plus 5x squared minus 4x minus 3 as the product of x minus 1 times 2x squared plus 7x plus 3. But now I can further factor this using the AC method. And so I can factor this into 2x plus 1 times x plus 3. And notice here I can still use that rational zeros theorem, and I can do p over q. My factors of P are going to be 1 and 3, plus or minus, and then my factors of the leading coefficient are going to be 1 and 2, plus or minus. So my possibilities are 1, 1/2, or 3/2, again, plus or minus. But I know how to factor a quadratic. Let's look at another example here to show you how this works. If I have the polynomial g of x is equal to 27x to the 4th minus 9x cubed minus 33x squared minus x minus 4. Remember, P, my factors, I'm going to list my factors of 4, are going to be plus or minus 1, 2, and 4. Q, I'm looking at 27. My factors are going to be 1, 3, 9, 27. So my possible zeros are going to be plus or minus 1, 1/3, 1/9, 1/27, and then 2, 2/3, 2/9, 2/27, and then I have 4, 4/3, 4/9, and 4/27. Now that's a lot of zeros to check, but it's way easier from starting with no options of what to check. Some tips: always start close to 1. So I'm going to start with 1, use synthetic division. So I've got 27, -9, -33, -1, and -4. When I do my synthetic division here, I end up with 18, which leaves me with -15, which leaves me with -16, which ends up with -16, which is not 0. So I know that 1 is not a solution. Well, I'm going to check -1. When I plug in -1 using synthetic division, I have 27, -27, which leaves me -36. Sorry, this was a 33, which leaves me with 3, giving me -3, -4, which is +4, and that is 0. So now I know one of my factors is x plus 1 because my -1 is a solution. I can therefore now write this as x plus 1, drop my degree 1, this becomes x squared, x cubed, times 27x cubed minus 36x squared plus 3x minus 4. Just because a factor has worked once, so -1 worked in synthetic division, I still need to check it again because it could be a double root. So now I'm just looking at this. I'm going to check -1 again. I have 27, -36, 3, and -4. When I pull down 27, I get -27, which is -63, +63, which gives me 66, gives me -66, which is not 0. But now I can check, say, 2. Again, I'm just checking it in that second factor that I had now. I get 27, 54, +18, 36, 39, 78 does not, so 2 doesn't work. I keep going down my list and it is tedious. I'm going to check 4/3. I get 27, -36, 3, and -4. When I substitute that in, I end up with 36, which is 0, which is 3, and I end up with 4 here, which is 0. So now I know my factors from up here. I still have x plus 1. This tells me I have x minus 4/3. And then that leaves me with this is my constant. This is x squared. So I have 27x squared plus 3. That's a quadratic now that I can simplify. And if you simplify all that out, you end up with 27 times x plus 1 times x minus 4/3 times x minus I/3 x plus I/3 is your factored form.